Good evening.
Good evening, ma'am.
Okay. So last class we were talking about TGA, that is thermogravimetric analysis, and in today's class will be also we talked about DTA, that is differential thermal analysis in last class. We'll just have a recap of DTA and then we'll proceed with DSC and thermometric titrations today. So now TGA particularly, that is thermogravimetric analysis, the plot of TGA represents the amount of mass change with respect to temperature. Now DTA, that is differential thermal analysis, the plot represents delta T in y-axis, that is the change in temperature versus the temperature range in the x-axis. So in the figure 11.1, it shows a typical DTA curve, that is a typical differential thermal analysis curve, where you can see that in x-axis delta T is plotted, whereas in y-axis we plot only T. Whereas in thermal gravimetry analysis, that is only TGA, in y-axis we have the mass loss, whereas in x-axis only the temperature is plotted. Now when we look into a particular DTA curve as shown in figure 11.3, so here we can find a point C in the plot. Now this peak, the C peak, is due to the exothermic peak, whereas and it points upwards in the endotherm in the curve, and the point F in this plot, it represents the endotherm, that is which points downwards. So this is the typical assignments of the endothermic and exothermic peak in a DTA plot. Now this we had already discussed in the last class, and we have a very important equation, that is for the calculation of peak area in a DTA, which is given as plus minus delta H into M into K. Now here delta H is 0, that is the enthalpy, change in enthalpy. It is positive for an endothermic reaction and it is negative for an exothermic reaction. M is the mass of the substance and K is called as the calibration factor, and it is particularly dependent on the temperature. Now here from this peak area and using the value of delta H in equation 11.1, we can use this for the calculations in change in delta heat capacity, that is delta Cp. It can be calculated as delta Cp is equal to m by heating rate, or mostly we use d by d of change in temperature with rate into 1 by m, which is given in equation 11.2. Now with these equations, thus from a DTA curve, we are able to find out the peak area, the enthalpy, that is the change in enthalpy, that is delta H, and we can also find out the change in heat capacity, that is delta Cp. So thus DTA is particularly useful in calculation of Cp and delta H. This we had known. Now we'll just have a recap about the instrumentation of a DTA. It mostly consists of five basic components, that is a furnace assembly, the sample and the reference holder, the temperature control, the amplifier and recorder, and the atmosphere control for the sample holder and the furnace. Mostly here the sample recording is carried out in an inert atmosphere, such as mostly nitrogen. Sometimes oxygen is also used, but an inert atmosphere is usually preferred. So now then there are certain factors which lead to the in which impact the DTA curves. Now because since it is a dynamic temperature technique, so these two factors can be divided broadly into two classes. One which is called as the sample factors, and the second factors that arises due to the instrument. So the instrumental factors, it includes the shape and size of the sample holder, the material of the sample holder, the heating rate of the sample, the sensitivity of the system, the location of the thermocouple, and the use of the gas, inert gas, in maintaining the environment or inside the instrument. So these are certain instrumental factors that impact the curve arising from the DTA measurements. Similarly, there are other factors which we collectively call as sample factors, and that include the type of the sample, the amount of the sample, the particle size of the sample, the degree of crystallinity, the dilution factor of the sample, and if we consider polymers, the swelling and shrinking rate of the polymers are also considered. So, such factors they contribute to the measurements of the DTA, and subsequently the curves are influenced accordingly. So now with the figure here in table 11.1, the factors that influence DTA curves have been represented and the corresponding suggestions have been made to rectify those lacuna. Like if the heating rate can be can be influenced by the effect is shown in the change in peak and position, and it is suggested to use a low heating rate. So for a particular, when we use an sample which does not contain uniformity in the particle sizes, then what we observe is irreproducible curves and very anomaly in measurement in the DTA curve. So it is recommended to use uniform sized particle. So these are some of the factors that have been listed. Now, although the DTA is quite efficient and measures accurately, there are certain errors it arises in the measurement of DTA. So one of the conditions is called as Buoyance effect. Now this arises when a thermally inert crucible is heated when it is empty, but there is certainly some amount of mass change occurs as the temperature is increased. This change in the mass when an empty crucible is heated is sometimes called as buoyancy effect, and this is due to the environment of the gases around the sample. Now, so this error it has been minimized or it has been neglected by first performing a calibration curve. That is, first a blank run is made using an empty crucible, and then the measurement is recorded by taking the sample. So this buoyancy effect can be removed in this manner. The second error that can commonly occur during the DTA measurement is the condensation on the temperature sensor. Now, when we take certain samples and they condense on the thermocouple, so then certain challenges arises. So, in order to totally avoid this situation, we can maintain a dynamic atmosphere around the sample mostly by using the we can using a dynamic atmosphere, particularly an inert atmosphere is maintained within the sample. So then there are other errors that arise due to fluctuation in the thermostat reaction, if there is a reaction between the sample and the container, if there is a turbulence effect of gas flow. So these are the certain errors that can arise during measurement of DTA, and they may be properly eliminated by handling the instrument properly, by maintaining an inert atmosphere inside the instrument and during the manufacturing process. So these are the certain errors, and the following remediation processes can be made. Now coming to interpretation of a DTA curve. Now as we know, a DTA curve, in a DTA curve, we measure the change in temperature, that is delta T, versus the sample temperature from which it is scanned. So in x-axis, it is delta T, whereas in y-axis it is temperature. Now if we look into figure 11.5, it represents the DTA curve of calcium oxalate in an oxygen atmosphere. So in DTA curves, particularly, they are the characteristics of a particular compound. So using DTA curve, we can relate the energy changes that occurs due to the thermal and chemical changes that occurs upon heating the material. Now this also provides us about the physicochemical transition that occurs within the compound. So the changes in DTA curve also gives us information about various crucial factors like the melting point, the glass transition temperature, the crystallization temperature, and the oxidation temperature. Now, so in order to understand this, let us consider the example of calcium oxalate, hydrated calcium oxalate, and the DTA curve is shown in figure 11.5. The measurements have been taken in presence of oxygen. Now, if we look into the curve, we can see three major DTA peaks in figure 11.5. Now, the first peak is, since it is downward, it is endothermic in nature. The second peak, since it is upward in nature, so it is exothermic in nature. Whereas the third peak, as you can see, it is downward in nature, so it is an endothermic reaction. So these results, if we look into the nature of the reactions, we can finally see what is happening in the decomposition of calcium oxalate when it is heated. Now here, from the figure, in the first endothermic reaction, the water of hydration is removed from calcium oxalate. CaC2O4 dot H2O is first forms CaC2O4, that is calcium oxalate plus water. So upon heating from a temperature to 400 to 600 degrees centigrade, we find a maxima at around 500 degrees centigrade, where this calcium oxalate, it reacts with the oxygen. Since oxygen atmosphere is maintained within the instrument, it forms calcium carbonate, 2CaCO3. Now in the third step, this calcium carbonate, it undergoes decomposition at around 750 to 800 degrees centigrade to form calcium oxide and carbon dioxide. So from this plot in 11.5, we can know the thermochemical changes and the physical changes that occurring inside the DTA in presence of oxygen from the temperature range 100 to 900 degrees centigrade. Now, here we can also find out the peak area of the each endothermic or exothermic plot that we have used in equation 1, that is peak area is given as plus minus delta H m into K, where K is the calibration constant at a particular temperature. Now we have, considering all the factors, we can write m1 by m2 is equal to a1 by a2. So using this equation, m2 is equal to m1 into a2 by a1. So using this equation, we can find out the area of an unknown sample. Here m2 represents the mass of an unknown sample, m1 represents the mass of a known sample, and a represents the respective peak areas. So using this equation, the unknown, the mass of a unknown peak area can be known. So similarly, the heat of reaction can also be known using the equation that we have derived for delta Cp. So this is how DTA has been useful for measurement of mass, unknown mass, and delta Cp. Now here, the if we look into figure 11.5, we can see, suppose we look into figure 11.3, that is shown here. So here, if we look into the figure 11.3, which represents a characteristics DTA, here we find out that the baseline should always be constant during the D2A measurement. Here in figure 11.6, we notice that the initial and the final baselines, they do not coincide. So therefore, the determination of peak area might be difficult. So to resolve these problems, first both the baselines, they are extended to a particular line drawn from the maximum of the curve to the area under the two halves. So using this formula, the heat of reaction, it can be further used to calculate it, and that is given as delta Hm is equal to delta Hr into Mr by M, whereas delta Hm, it represents molar enthalpy of the reaction, delta Hr is equal to enthalpy of the reaction, Mr is equal to the related molar mass of the compound, and M is the small m is the mass of the substance that we have considered for the DTA measurement. Now, determination of heat capacity. The DTA curve, it is very particularly used for measurement of delta Cp. For this purpose, a DTA curve is first recorded in an empty container, and then the container is recorded in the identical condition. So the absolute changes in temperature, that is delta Tx, is measured from the following equation, that is Cp is equal to K into T2 minus T1 by M into H, where Cp represents the heat capacity at temperature T1 and T1 and T2, they are two different temperatures when they are generated when the instrument is run without any sample, and then the second temperature is generated when the sample is taken inside the instrument. H is the heating rate and K is the calibration factor. Now it can be determined by calibration against standard substance of known enthalpy change. The construction of phase diagram using DTA curve. The melting point can be known by the DTA curve for a eutectic mixture of different sample with variable concentration composition. The melting points can be used to construct a phase diagram. So the determination is used of a cooling curve. A discontinuity is observed at the critical temperature. So at the and critical temperature is represented as Tc. The Curie point temperature, it suddenly changes, also makes it suddenly changes at this point, and it has been determined by this technique. So this phase diagram can also be constructed using DTA curves, and it has also been helpful in the determination of critical temperature, that is Tc. Then comes the estimation of transition temperature. The determination of transition temperature of a precision of almost zero point 0.3 degrees centigrade can be made from a DTA curve. The temperature estimated, that is MP, that is melting point or boiling point, have most often been selected from the particular peak, and then we extrapolate the data from there. So when we look in, the melting point is measured by using is measured by using the sample which is closest to temperature C, and for the temperature B. In many cases, as we look into figure 11.7, we can see various different temperatures at different points. Whereas, so to actually find the melting point of the particular sample, it is measured by using the sample which is closest to the temperature of point C and temperature at point B for reference. So in exceptional cases, it has also been found that Tm might be closer to the point D. So there are now comes the certain applications of DTA. So DTA have been used for quantitative and qualitative identification of various types of minerals. For the detection of any minerals in a sample, it is very important that we understand the energy changes that is occurring inside the mineral. So oxidation and reduction and other reactions are happen during the thermochemy, when temperature is changed or when heat is applied to the substance. So however, if we look into this and we plot the DTA graph, then we can find out the exact changes happening at the exact temperature. However, we often encounter certain difficulties during the measurement process, but still DTA remains a very helpful technique. Now if we look into figure 11.8, so here three different samples have been given. One is for kaolinite, the second is for montmorillonite, and the third is for illite. So here is that if multiple peaks are present. Now if we look into kaolinite and illite, they are almost present in the same sample and almost overlapping each other. From the peak shown in 11.8, we can find that none of these miners, they show an exothermic peak corresponding to organic mentioned above. So here the figure B and C, and if we look into them, all the temperatures are same to each other. So therefore it is quite difficult to measure the exact TG, that is the grass transition temperature, for all these samples. Now coming for polymeric materials, TTI has been very useful for characterization of polymeric materials, for identification of their TG, that is the glass transition temperature, TC, that is the crystallization temperature, TM, melting temperature, and oxidation, that is TD respectively. So these are the four types of temperatures that can be measured from a DTA of a polymeric sample. Now if we look into figure 11.9, we can find that the graph particularly, it shows the Tg, the Tc, the Tm, and the Td of a polymeric sample, whereas the glass transition, the crystallization temperature, the melting temperature, and the oxidation temperature. So, with the help of this, the unknown polymer, it can be characterized by these techniques. So the DTA technique is also, it is useful for analyzing a polymeric mixture both quantitatively and qualitatively. So the individual polymers that are taken in a mixture, they have their own Tg and Tm. So from by matching the values that is obtained in our case, and with that of the reports, we can find out the actual polymer that is present in the mixture. So here in figure 11.10, we can see the various types of polymers are taken and their respective peaks are shown. So it shows characteristics peaks of all the polymers, and hence the presence of individual polymers are identified from the DTA curve. The area under the peak is related to the heat of reaction, the DTA of one of the areas, and from this 11.110 we can find out the exact individual polymer that is present in the system. The another important parameter that is determined from DTA is Tg, that is called as the glass transition temperature. Here the first glass transition Tg detection was done in 1957, where a transition at 28 degree was shown but not interpreted. So the relation between Tg, that is glass transition temperature, and Tm, that is melting temperature, has been found to be Tg by Tm is equal to 0.66. This is one of the commonly used conversion for Tg and Tm. The glass transition of a polymer has also been used from the following equation that is given here. The deduction of the slopes of the glass transition as depicted by DTA, it shows that the slope of the curve delta T surface, it should be sigmoidal in nature. The So as we are talking, the DTA results, they provide important information about the polymerization reaction, the degree of polymerization, the decomposition reaction, and other reactions that occur during a polymerization process. Now, the degree of the DTA has been particularly useful for measurement of crystallinity, and it is particularly applicable for polymers. The method is based upon the measurement of the delta HF, that is the heat of fusion of the polymer, and its assumption that this quantity is proportional to its crystalline content. So if to find out the delta HF for a polymer, we need two factors, that is, and we it is assumed that delta HF, that is the degree of heat of the fusion, change in heat of fusion of a polymer, is directly proportional to the content of that is the crystalline content that is present inside the polymer, which is delta HF star. So the mass fraction is given as delta HF by delta HF star. Thus, the crystallinity of a polymer, which is represented as chi, can be used as by measuring the total energy absorbed by the sample per gram, that is delta H, and subtracting the amount of energy, which is given as X is equal to del H minus del HF A by delta HFC, where A represents the total amorphous material and C represents the amount of crystalline sample present in the material. So another method of determination of polymer crystallinity is based on the ability of the instrument to cool a molten sample readily and measure the temperature at which isothermal crystallization occurs. However, the number of crystallization curves may be obtained at different temperatures. The difference in crystallinity has been caused due to branching, nucleation, and various molecular effects. So, we know that the degree of polymerization can be measured from DTA curves. Now here in table 11.2, we see the estimated heat of polymerization that has been found from various DTA curves, and it has been reported for trialkyl cyanurate and triallyl isocyanurate. So further, the size of the peak in DTA curves is also, it is also has a greater impact in assess the degree of curing that occurs during a polymerization reaction. Now coming to the analysis, the utility of DTA curves in analysis of biological materials, the DTA has also been profoundly used for to understand the thermal characteristics of biological molecules. So it describes the various components, the non-homogeneous materials which exist in correlation to other homogeneous substances present in biological states. However, the investigations that are carried out under experimental conditions, it indicate that DTA curve should be of value as fingerprint of biological materials. The thermal characteristics of a number of biological materials have also been studied under different atmospheric conditions. Now, fresh biological materials that consists of matters of active body and plants, they have also been studied by DTA. However, it is also always difficult to find out the exact chemical constituents and the thermal properties of plant materials. Now, the information that has been obtained has not been directly indicated to a homogeneous biological material. So, like in one study of indirect system, the DTA curves of four different leaf samples of different plants in oxygen environment was studied, and it was found that it has pronounced exothermic effect in the range of 240 to 270. So the first peak was found to be smaller and the second was found to be higher in peak height and peak area. So although there could not be established the general similarity in these curves, it indicated that the in all the four cases, the DTA curves were identical in nature, and it was inferred that they might have some of the components which are similar in all the cases. Now, the DTA curves for some plant materials have also been studied in static or air or at oxygen atmosphere, since it is very difficult to understand the decomposition oxidation effects which overlaps in an oxygen environment. The endothermic reactions such as dehydration or volatilization, while exothermic accompany combustion under inert atmosphere conditions, they all can be detected. Similarly, the analytical method has also been used for high energy materials, explosives, ceramics, plants, cements, and pharmaceuticals. Now, these are some of the applications of DTA. Now, coming to DSC. DSC is also one thermal measurement technique. This is called as differential scanning calorimetry. This is also a very simple technique, and it has been in contrast to DTA scheme where both sample and reference, they are heated by the same source, whereas in DSC we the typical curve of a DSC that is shown in figure 11.11, we can find the DSC measures the heat flow, that is delta H versus T in a reaction. So now, if we look into the working principle of a DSC, the heat flow here is measured and plotted against temperature versus time to get a thermogram. Now, this is the basis of DSC, where the y-axis it measures the delta H, or we can say dH by dt, versus the temperature that is taken in degrees centigrade in the x-axis, now as shown in figure 1.11.11. Now the area under the peak, it is directly proportional to the heat evolved or absorbed by the reaction, and the height of the curve is directly proportional to the rate of the reaction. So therefore this equation 11.11 is equally valid for DSC scheme also. So the only difference that we understand is the calibration factor K in DSC and DTA. So, and this K in case of DSC, it is not dependent on temperature. However, when we have talked of DTA, the calibration factor K is temperature dependent. So, this is a major advantage of DSC over DTA because the K remains independent of temperature in DSC, whereas it is temperature dependent in DTA. Now coming to instrumentation of a typical DSC instrument, the block diagram here it has been shown in figure 11.12. This is the block diagram of a DSC. It represents the basic components of a DSC instrument. So here it basically works on the temperature control of two similar specimen holders. The left half of the block diagram, it represents the circuit for differential temperature control, while the right part, it indicates the average temperature control. Now, when in the average temperature control circuit, the temperature of the sample and reference are measured and averaged, and the heat output of the average heater is automatically adjusted so that the average temperature of the sample and reference they increases at a linear rate. Then the differential temperature, it uses the control circuit monitors to difference in temperature between the sample and the reference, and then automatically it adjusts to keep the temperatures equal. Then we get a thermogram. For getting a thermogram, the temperature of the sample is put on the x-axis, and the difference in power, that is delta H of the two differential heaters, is displayed on the y-axis. In figure 11.12b, the individual two heaters have been shown, which illustrates the heating arrangement in sample and reference compartments. The sample and the reference compounds, they are provided with their own heaters, like in their own compartments, as well as both their sensors, so that their S and R are identical. They remain identical by controlling the electrically by rate at which the heat is transferred to them. Now here when we look into the heating arrangement, both the sample and the reference, that is the S and R, they have been given their own compartments, and the heating is done and their individual heaters are provided to them, which maintain or regulate the temperature in them. Now during the thermal process, here in the DSC sample, the samples mostly range from 1 to 100 mg. They are placed in sealed sample containers. The heating rate for has mostly been like zero point 0.5 to 80 degrees centigrade can be used. DSC instruments, they are generally very sensitive and they detect heat evolution or absorption at a rate of less than 1 millicalories per second. Here the electrical signals, then they are amplified and recorded like similarly to TGA and DTA. Now, during the thermal processes, what happens is the heat is either absorbed or it is liberated. So, thus, when delta H is positive, that is for a endothermic reaction, the sample heating device is positive in nature, and thus a positive signal is obtained. Now, when delta H is negative, that is for an exothermic reaction, a negative signal is obtained. So an idealized representation of the three major processes, here it is given in figure 11.13. The peak area in DSC, they are proportional to the amount of heat, the heat of the reaction, and it is given here. In figure 1.11.13, we can see that here delta H, the figure plots delta H in the y-axis, and temperature has been taken in the x-axis. The C represents the exotherm and the F point, it represents the endotherm. The peak area is calculated using the equation A is equal to plus minus delta H mk, where delta H represents the enthalpy change and m is the mass of the sample and k is the calibration factor. But here in DSC, the calibration factor is dependent on temperature. The unlike DTA, it is independent of temperature. So using 11.16, we can determine the delta H of a reaction, and also we can find out the peak area provided we know the value of K. Now we can also determine the enthalpy change using this equation, that is delta Hs, that is the enthalpy change of the sample, is equal to AK Mk into delta Hs by As into Ms, where delta Hk, it represents the enthalpy change of the sample. Delta Hs represents the enthalpy change of the known sample. The Ms and Mk are the masses for the sample and the known standard, and A represents the peak area, whereas As is the peak area for the known sample, and K represents the peak area of the standard material. So substituting the exact values at equation 11.7, we can know the delta H of our sample. Now, this DSC technique is not only sensitive for the determination of delta H, but it is also very sensitive for the determination of Cp, that is delta Cp, or we call it as heat capacity. So, this may be detected by the displacement of baselines. Now, we have the value of Cp can be determined at a particular temperature by measuring the displacement, and it is invariably given as Cp is equal to, here it is given as Cp is equal to dH by dt by d of t by dt into 1 by m. So using equation 11.9, we can find deduce the unit of Cp. In DSC curve, the displacement will be measured in millijoules per second. So if the heating rate is in delta centigrade per centimeter second and m is expressed in grams, then the Cp, unit of Cp, is given as mj per gram per centigrade. Sorry, here Cp, it can also be expressed in terms of calories, and since the conversion factor for joule to calories is 1 calorie is equal to 4.2 joules, and here the total can be also calculated in terms of calories. In practice, we normally measure the baseline shift by reference to a baseline obtained for empty sample and reference pans. So we have a calibration curve, and that calibration is given by equation 11.10, where k dash is k dash into h2 minus h1 is equal to m into cp dt by dt. So here h1 and h2, they are the heat generated when the instrument is first run without n sample, and then when the instrument is run without n sample, and when h1 represents, h2 represents when the instrument is run taking n sample with it, and k dash here, it represents the calibration factor which can be determined against the standard. However, the k dash, that is estimated from 11.10, it can be eliminated if it has very negligible value. So one of the most commonly used standard is alpha aluminum oxide or alpha alumina or synthesized sapphire, for which specific heat it has been determined to 5 significant digits ranging in the temperature from 0 to 1200 K. So at any temperature following the following equation, it applies K dash T dash is equal to M dash Cp dash into dt by dt. So from this equation, we can find out the value of, here in equation 11.12, the d and d dash, they represent the displacement, or we call it as the ordinate deflections that occur due to the sample and our standard respectively. The m dash cp dash, they are the mass and heat capacity of the standard. So dividing both this equation, we get a very common equation, that is Cp by Cp dash is equal to dm dash by dm. So this calibration, we can easily, using this equation, we can easily calculate the value of Cp on substituting the exact values at the exact places. The basic components of a DSC, it is quite similar except the differential energy measuring system. So in DSC, basically two principles are followed. One is based on the power consumption and the other heat flow method. So in the power compensation method, smaller secondary heater, they are attached to two equalized the generated energy difference between the sample and our reference. While when we consider the heat flow method, here the heat flux passing through the sample and the reference, they are evaluated and the difference is related to their energy consumed, that is either consumed or released during the thermal reactions. So in general, this is how the basic principles, working principle of a DSC. So now coming to the various factors that affect the DSC curve. Now first, when about during we start a measurement, DSC measurement, the TI, that is the initial temperature, or it is most commonly called as the onset temperature, it is can be detected by the instrument operating under particular conditions. We may like to call it as the transition temperature. However, in DSC, TI, TF, and TC, they are very important while indicating these temperatures in a DSC curve. The term procedural thermogram is often used for the temperature at which the temperature change begins to appear. This indicates the start of a reaction, which is usually called as the onset temperature. The temperature does not have a fixed value, but it depends on the experimental procedure to get it. Similarly, there are many factors which influences the temperature and the corresponding DSC plot. So the three main factors which affect the shape, precision, and accuracy of a DSC curve have been categorized as instrumental factors and sample factors. So the instrumental factors, it comprises the heating rate, the recording, the furnace atmosphere, the geometry of the sample holder or the location of the thermocouple sensors, the sensitivity of the recorder, and the composition of the sample container. Whereas the sample factors that contribute to the overall DSC graph, it includes the amount of sample, the solubility of the different gases that come out during the DSC measurements, the particle size, the heat of reaction, the sample packing, the nature of the sample, and most importantly, the thermal conductivity of the sample. So these are the various factors which influence the shape, the precision, and the exact measurement of a DSC plot. Now, there are various number of sources of errors in DSC that can arise during a DSC measurement, and thus it can lead to inaccuracies in our recorded data. So some of these errors, they may be corrected in the lab by proper handling of the instrument, and other errors, they are quite common during except during operation, and they can also be, however, the errors that arise due to the use of the secondary heaters and thermostats cannot be actually, that those are manufacturing defects and that has to be corrected from the manufacturer. Now the errors can be avoided by proper placing and handling in the laboratory, the maintaining the optimum temperature, and having a constant power supply. By avoiding excessive heating rate and proper gas flow and maintaining a proper gas flow rate, these errors, other errors arising, can be avoided. Now, to further minimize the errors that might appear during the measurements, the instruments must be, the DSC instrument must be calibrated, and the peak area measurements must be optimized with a standard. The difference between the calibration constant in DTA is temperature dependent, whereas in DSC it is temperature independent. So therefore in DTA measurement we should calibrate peak areas using a standard which provides a reference peak in the same temperature as that of the test sample. Whereas in DSC, now we know that K is independent of temperature. Therefore, it requires just very fewer steps for the simple calibration of the instrument. Now, for peak area calibration, we need standards of high purity and accurately known delta HF. Some commonly used calibration standards for DSC, they are indium, benzoic acid, tin, lead, silver, and gold, which are most commonly used for calibration in DSC. Now coming to interpretation of a DSC curve. Now as we have seen the interpretation of a DTA curve, the interpretation of a DSC curve also shows the various behavioral changes that occurs in a material with respect to temperature. Now the DSC curve, it is also referred to as a fingerprint of the compound in context to its glass transition temperature and melting temperature. Therefore, DSC is also gives us much information about the thermal behavior of a material. So here we have seen that known that the area under DSC, it is related to the amount of delta H, that is the change in delta H, which reflects its physico-chemical change. Now here in figure 11.14, the DSC curve of a polymeric mixture is shown and the probable transitions have been shown here. Now we can see in the DSC curve various types of transition are occurring. This technique is more sensitive as we can know the glass transition temperature, that is the TG, the melting region, that is the TM, followed by the degradation behavior of the polymer. So this TSC technique, it is more sensitive than DTA and it provides a clear indication of the thermal events that occurs within the material with related to temperature. Thus, the information that is provided by the DSC, it is more realistic in nature. So DSC is used for to know the presence of polymorphism, the degree of crystallinity, the curing that occurs during a polymer during the heating process. So the heat of the reaction, that is delta HR, observed in DSC, it is further, it can be used to calculate delta HM, that is the molar enthalpy of reaction, by the following formula, which is given as delta HM is equal to delta HR into MR by M, where delta HM represents the molar enthalpy of the reaction. Delta Mr is called as the relative molar mass of the compound, that is our test sample, and small m is the mass of the substance that we have taken for analysis. So from this equation, delta Hm, that is the molar enthalpy of reaction, can be calculated from a DSC plot or a DSC thermogram. Now they're coming to various applications of DSC. DSC is particularly used to measure the change, energy change, that is delta H, as a function of temperature or time. So using this technique, it is possible to observe a number of characteristics properties of the thermal characteristic properties of the sample, such as the glass transition temperature, TG, the fusion, the melting temperature, that is the TM, and other reactions. In certain cases, oxidation has also been studied from DSC. Now, these transitions that happen within the material and that are responsive to the particular temperature. So, as the temperature increases, an amorphous solid, it becomes less viscous. After some time, these molecules, they obtain enough energy and then they convert to a crystalline form. This particular temperature is called as the crystallization temperature, or and it is represented as TC. So this transition from amorphous solid to crystalline solid, it is mostly an exothermic process and it results in a DSA signal. So as the temperature is increased further, the sample, it reaches its melting point and thus the melting temperature of the sample is indicated, that is Tm. The melting process, it results in an endothermic peak in the DSC curve. Thus, the ability to determine the transition temperatures and enthalpies in a DSC is very sensitive and it makes DSC a very important tool to understand the various phase changes that is occurring within a material. This equipment, it is quite easy to calibrate. It has since indium is low used as a standard, it has a low melting temperature, and there are few notable specific applications of DSC, such as the result of a DSC experiment is a curve of heat flux versus time, that is delta H versus temperature. There are two different conventions: exothermic reactions which is shown as a exothermic and endothermic reactions. Now we can know that the enthalpy of transition is known from this equation. Delta H is equal to K into A. So where delta H represents the enthalpy of transition, K is the calibration constant, and A is the area under the curve. So mostly by using this equation, the known enthalpies, the unknown enthalpy of the transition of a reaction can be known. So most of the well-known specific spectroscopic methods, they are like quite important in qualitative and quantitative analysis of chemicals, and they are mostly based on the principle of the absorption or emission caused by the transition of energy from one state to another. This great potential has been used, it has been exploited for thermal spectroscopy, and many materials it can exist in more than two or different crystal forms. So therefore we can say that from DSC we can actually know, by looking into the TG and TM, we can know that which material, the exact crystalline phase of the material that it is presenting. Now DSC has also been used in the study of liquid crystals. Now, as matter transitions between solid and liquid, we know that it goes through a third state. So, where it displays the properties of both solid and liquid phase. This phase is known as the liquid crystalline or the mesomorphous state. So using DSC technique, we can find has been possible to find the small changes that occurs as a matter of transitions from solid to liquid or from liquid to crystal through this process. So this is how DSC is used in the study of liquid crystals. So I'll be just back in 2 minutes. Sorry for the inconvenience. So we were talking about the utility of DSC in the study of liquid crystals. Now DSC curves, it has also been used to understand the purity of drug and polymer interaction. This is possible when we understand the temperature range over which both the drug and polymer melts, and we can find out the amount that of the drug that goes into the polymer. So when we take, if we look into the TM particularly, the TM of the polymeric material, it reveals the amount of the drug that has been in reaction with the polymer, and then we can find out from the value that the degradation behavior of the polymer and the melting point of the polymer inside and the drug from the DSC curve. Now in pharmaceutical industry, it is necessary to have well characterized drug compounds, that is for various purposes. So there are two important criterion for characterization of waxes and fats by DSC. Although the melting shape of wax and wax formations are quite complex, they are much less sensitive to variation in crystallization, and the crystallization of waxes is usually nucleated with the result that solidification occurs. So using DSC, we can study the TG and TM of waxes and fats that are crucial to mankind. So, using DSC, it has the oxidative stability of samples have also been studied at airtight chamber. So, more specific application of DSC where DTA cannot be applied is the detection of magnetic transition in materials. The magnetic transitions, they are of second order where delta H is equal to 0, but with a maximum heat capacity at the transition temperature. This technique is sensitive to detect these minor variations. A typical DSC curve for a magnetic transition has been shown here in figure 11.15. So similar glass transition can be easily from this figure, such glass transition can be detected easily with DSC. So in general, So we can say that DSC has been particularly useful for various fields in the analysis, starting from liquid crystal to polymers to understanding drug polymer interaction to understanding the TG and TM of waxes and fats, and also in the analysis of various magnetic transition in various materials. So now the advantages of DSC. DSC particularly utilizes very small amount of sample, that is ranging from 1 to 10 mg. The procedure is very simple and it mostly depends upon the heating rate. Usually the heating with a heating rate of around 10 to 5 degrees centigrade, the measurements could be completed in 15 to 30 minutes. This is DSC is ideal for comparison of sample purity in quality control analysis. It does not require any high temperature for absolute temperature accuracy. It does not require calibration with known impurity levels. The cryoscopic constant is obtained simultaneously. The use of melting here rather than a freezing curve, it avoids the problems associated with the cooling of the sample, such as supercooling of the sample, the poor recrystallizability for the melt, and the instability of the melt. So here we can see these are the certain advantages of DSC over DTA, and therefore DSC finds more applications in thermal analysis of materials than in DTA. Now coming to thermometric titrations. So before going for thermometric titration, I'll just take a break of 5 minutes, then again resume. So now coming to thermometric titrations. So now we all know the difference between TGA, that is thermogravimetric analysis, DTA, that is differential thermal analysis, and DSC, that is differential scanning calorimetry. So now applying all the principles of these three instruments and the concept of thermogravimetry, we will go for understand what is thermometric titrations. So in principle, we have the similar to thermogravimetry, which is based on the principle of thermometric titrations. Here the principle of thermometric titrations is based on the change in temperature with the addition of titrant and the determination of the end point from a plot which plots temperature versus the volume of the titrant that is used. So basically the plot here, as it is shown in figure 11.16, the y-axis, it measures the temperature, and the x-axis, from the x-axis, that is the volume of the titrant that is added, we can find out the endpoint. And this particular plot uh, are is actually called as a enthalpogram, and such type of titrations are called as thermometric titrations or enthalpy titrations. These titrations, they can be exothermic or endothermic in nature depending on the type of the titrants and the sample used. In such titration, the change in temperature, it occurs only when the titration is in progress and the reactant is present. So thus start and the end point of the titration, they are usually observed quite easily, and the number of the moles titrated is calculated in regular fashion. So by determining the heat capacity of our system under consideration, the heat of the reaction can be easily determined. In addition, the equilibrium constants can also be evaluated from the experimental conditions and substituting the appropriate data. So here in figure 11.16, a typical enthalpogram is shown. So on both sides of the enthalpogram, the baseline, it represents the temperature line blanks recorded prior to the start of the titration. Here the B corresponds to the beginning of the addition of the titrant, and C is the indicator. It actually indicates the endpoint or the equivalence point. Thus, here BC is the titration branch of the enthalpogram. So, in cases where delta H is less than 0, it has an ascending slope, whereas in cases where delta H is greater than 0, it has a descending slope. So, in figure 11.6b, here in this figure, we can see both cases the excess reagent, it branches the enthalpograms, and they cause, because the dilution of most of the titrants is an exothermic process. So in order to minimize the variations in heat capacity during titration, mostly it is advisable to use the titrant which is 550 to 100 times more concentrated than the unknown titrated. So thus, so from all this equation we have an important equation which is denoted as delta T is equal to Q by K, or that is equal to minus N into del H by K, where K is the effective heat capacity, N is the number of the moles that is reacted in the titration. From this equation, we can the quantity BB dash, that is extrapolated from the graph, and it can be used for obtaining the various information such as the heat of the titration whenever a known amount of titrate is used. From this equation we can also know the concentration of an unknown titration whenever delta H is known, and we can also know the quantity of an unknown in a known volume of a titrate. So this is how thermometric titrations are made. The nomenclature of a thermometric titration is sometimes a bit confusing. So, enthalpograms are thermometric titration curves where temperature is observed well upon the addition of a titrant. This basic property, it usually determines the shape of an enthalpogram, or it indicates the change in enthalpy. So thus we usually say it as thermometric titration or enthalpy titration. However, similar terms it include calorimetric titration, thermocalorimetric titration, thermal titration, and sometimes thermochemical titration has been used. So, and these are certain the nomenclature that has been used for TT, that is thermometric titration. So another type of thermometric titration, it includes direct injection enthalpymetry, that is DIE, which gives us a plot of temperature versus the time following the injection of the titrant. So in this case the endpoint is not obtained, but the magnitude of the temperature change is proportional to the concentration. The speed analysis is enhanced and the process with equilibrium unfavorable for titration, they are studied by using a large excess of one of the reagents. So now coming to the instrumentation process of a thermometric titration setup. So here the experimental setup, it consists of a reagent delivery system, motor driven automated burette, an adiabatic reaction cell such as Dewar flask with stirring device, an electronic temperature system, and an amplifying and data processing system. Here it is typically represented here in figure 11.17. So in a TT temperature control, that is in a thermometric titration, temperature control is most important and it is indicative of the results that is required. So often it is possible to obtain titration simply by bringing both the sample and the titrant to first room temperature. However, for precise calorimetric results, the titrant and sample they must be close temperature as far as this is possible by the help of a thermostat. Now, delivery pump, a constant delivery pump is used that permits the time axis of a strip chart, and it is typically a syringe driven by synchronous motors which drives the screw and is a solution ranging down to few micro ml per second. In DIE, the syringe is rapidly emptied at the start of the experiment to deliver the titrant instantaneous into the cell. Now comes the adiabatic cell. These have widely varying designs and they mostly a Dewar flask type is mostly used. All the cells they are designed to minimize the heat transfer from the cell to the environment, thus maximizing the temperature change that is observed. So now comes the calibration unit. So in order to bring the cell to thermal equilibrium, it is essential to use a calibration heater. It serves two purposes. First, it determines the heat capacity, and second, it controls the temperature within the cell. The heat evolved or absorbed is calculated from the change given by delta H is equal to del T into Cp dash, where Cp dash represents the heat capacity of the system, which is measured as the amount of heat necessary to raise the temperature of the cell by an unit. Now comes the temperature sensing system. It is the heart of the actual part of the thermometric titrator. The principal temperature sensor, it is a thermo resistor or a thermistor, which is temperature sensitive conductor whose resistance obeys equation 11.16, and that is given as R is equal to A into e to the power b by t, where b and a they are the constants and the values depends on the type of the thermistor. So a thermistor, it has the advantages of being a small size, fast response, temperature responsive, and also it is responsive to the chemical changes occurring within the environment. The next part, it comes as the amplification and the recording. So it is often useful to amplify the signal that is obtained from the thermistor. So a DC amplifier is used to obtain particularly good results for the temperature ranges of the order of 10 to the power minus 4 degrees centigrade or still less. So however, for lower temperature of order in the order of 10 to the power minus 6 degrees centigrade, a AC or a Wheatstone bridge with a lock amplifier is used. Now, the two most popular data acquisition systems, they are the strip chart recorder and the digital data storage system. So figure 11.19, here it shows the idealized representation of the four regions of the TT curve. So, and then with the help of a constant delivery pump, the moles in the x-axis, it can be regulated. Now, the experimental procedure for a for a thermometric titration. So an idealized thermometric titration, here it is as it is here, it is shown in figure 11.19. So here, so the region 1, it corresponds to the baseline, which is ideally horizontal, but actually in practice it has a finite slope because of the heat that is produced due to stirring, the resistive heat that is added by the thermistor, and the transfer of the heat from the cell to the thermostat. So if heat arising due to friction and resistance are constant and equal to W, then the slope of region I is represented as dt by dt. D of T by dt is equal to C into Tc minus Te plus W, where C is equal to the heat lock modulus, T represents the cell of the temperature, and Te represents the outer environment temperature. Now, in second region, if you look into figure 11.19, the second region, the slope is due to the similar effects as in region 1, and the following equation is given as by equation 11.18. So now coming to the region 3, equivalence point has been passed. If you look into figure 11.19 here, the equivalence region is passed, and the slope of the curve is described by the equation given in equation 11.19. So after this, there is no more titrant that is present, and in the slope 4, it obeys the initial equation that is represented in equation 11.17. So however, in real practice, a rounding is observed at the equivalence point, and this case is dealt in a separate manner. So the equations 11.17 to 11.19, they are all combined together to obtain the heat of the reaction delta H, and the K is calculated as del minus delta G is equal to epsilon K is equal to minus del H plus T del S. That is the general reactions. So for knowing the concentrations of the titrant or the sample, the concentration of the unknown may be calculated from the volume added to each point. So from the equations represented, and the value of delta G can be calculated from utilizing the above equations. Now coming to the applications of thermometric titrations, since the heat of the reaction is the most general property of various chemical processes, thermometric titrations, they have wide range of applicability, and particularly in qualitative analysis. So it includes the determination of the concentration of an unknown substance, the reaction stoichiometry, the equilibrium constant, and thermodynamic quantities such as delta G, delta H, and delta S. Now, these have also been applied successfully to various titration processes such as neutralization titrations, redox reactions, precipitated reactions, and complexometric titrations, from ranging in aqueous media from room temperature to 350 degrees centigrade. The lowest limit of concentration that can be successfully titrated is 10 to the power minus 4 molar. However, one of the main limitation of this method is that it is non-selective. The nature of information derived from the judicious mathematical analysis of titration curves have been summarized here in 11.2. So if we look into table 11.2, a summary of the application of thermometric titrations have been indicated. For normal fundamental type of titration, the heat of the reaction, free heat of the energy of the reaction, and the entropy of the reaction, they can be calculated from the extrapolated ordinate heights. If we want to know the reaction stoichiometry and the concentration of the unknown, they can be calculated from the dynamic equation, from endpoint determination, and direct enthalpy metric. So here, as we look into figure 11.20, a comparison of potentiometric titration and thermometric titration curves for HCl with and H3BO3 with NaOH solution here is given. So here the potentiometric curves for the two acids, they are very different, yielding a large inflection point. However, the corresponding enthalpograms that is shown in figure 11.20b, we find that they are similar to each other, and their heat of neutralization are comparable. So as a result, H3BO3 can be determined with better precision and accuracy by thermometric titration in comparison to figure 11.220a, by that is by potentiometric titration. So this is how the potentiometric titration is disadvantaged for the measurement of HCl and H3BO3 in NaOH solution, and thermometric titration is preferred. The thermometric titrations, it possesses extraordinarily potentiality for determining the heat of the reaction in a dilute solution rapidly and more conveniently, so that the delta H values, it can be set equal to ideal thermodynamic parameters corresponding to infinite dilutions. The non-aqueous solutions, they are particularly well suited for thermometric titrations through though the heat of mixing of solvent and the dilution, it poses a problem. Thus, under strictly anhydrous conditions, even diphenylamine, urea, acetamide, and acetanilide, they can be easily titrated with perchloric acid in glacial acetic acid. Lewis bases like dioxane, pyridine, and THF, they can be titrated with Lewis acids like SnCl4, NCCl4, benzene, and nitrobenzene. Thermometric titrations are very useful for titrating acetic anhydride in acetic acid, sulfuric acid, and acetylating bath in concentrated acid. So analysis of mixtures is possible when two species, they have different equilibrium constants and the heat of the reactions with the titrant. So here in figure 11.21, a typical curve for the thermometric titration of a mixture of Ca2 plus and Mg2 plus with EDTA is shown. Here the EDTA, it reacts first exothermically, shown at minus delta H is equal to minus 5.7 kilocalories per mole, and the magnesium, it reacts endothermically here with delta H is equal to 5.5 kilocalories per mole. So precipitation and ion recombination reactions by TT also yield very good results. So for example, when halide reacts with silver or mercury and cations such as Mn2 with EDT and oxalate, such titrations are preferred, and the curve from the curves, they can be easily estimated. Now, when we consider to determine the equilibrium constant of a complex formed by thermometric titration, let us consider an equation, that is A plus B forming AB. So when equilibrium concentrations can be calculated, we have AB. Looking from figure 11.22, we can see concentration of AB is equal to H by HT of A, where A is equal to A minus AB, and here B is equal to B minus AB. So considering the equations, the equilibrium constant is given as K is equal to concentration of AB upon concentration of A into B, and substituting the values of AB and AB, we find the equation 11.22. Now, if we consider a metal that forms a ligand and with that reacts with a ligand L to form Ml, so then the above value for the determination of the equilibrium constant K by the complex ion Ml, it can be used for the calculation of the stability constant K given by this equation. So, when dilute solutions are used, it may be safely assumed that the thermodynamic parameters, they are mostly same as the that of in the standard state. That is, delta H is approximately equal to delta HF0. So, using these values, the particular equations, we can find out the use of thermometry in estimation. So, today we have studied about the applications of DAC, DTA, DAC, and thermometric titrations, and for the calculation of the K from thermometric titrations. So with this unit, the this unit is over. That is the calculation DTA, DSC, and thermometric titrations. So now we will start with radioactivity. So now radioactivity, it is a totally different branch of analytical chemistry, and it is based on radioanalytical chemistry, which uses the principles of radiations that are emitted by different radioactive substances. Now, before going into the details of different radioanalytical techniques, let us understand what is radioactivity. So, radioactivity is the spontaneous emission of radiations which include alpha, beta, gamma, and other radiations from the nucleus of an atom. So the radionuclide that emits radiations may already be, it may be present in a sample, or it may be added from outside, or it may be bombarded in a nuclear reactor. So in essence, radioanalytical methods, they can be employed for the analysis of various, for even ultra trace minor amounts of samples present in different samples. So these radioanalytical techniques, they have been wide for analysis in geological and biological, environmental, and other processes. Since radioactivity, it is a nuclear phenomena, whereas other analytical methods are mostly electronic phenomena. So here, let us understand what is radioactivity and radioactive decay law. So atomic nucleus, as we know, it consists of nuclear particles, that is the protons and neutrons, which are combinedly called as the nucleons, whereas the exception being the hydrogen nucleons, which consist of a proton only. So these nucleons, they remain tightly bound inside the nucleus by strong nuclear forces, and they operate in the range of the short nuclear range of, like, the nuclear radius ranging from 10 to the power minus 15, that is called as 1 Fermi. So the sum of the protons and neutrons, that is n plus z, it, in a nucleus is called as its mass number, which is represented by A. So all the atoms whose nuclei contain the same number of protons, they have similar chemical properties. But atoms of the same element may have a different number of neutrons, and therefore their A values are different. So atoms that have the same Z value but they have different A values, they are called as isotopes. Each isotope, it has a fixed abundance in nature. However, we do encounter some few exceptions. The relative abundance of any isotope, which is usually expressed in terms of percentage abundance, is called as the isotopic abundance. So it indicates the abundance or the amount of the isotope that is present, relative abundance. So each element, it has two types of isotopes. One is naturally abundant stable isotope, and the unstable or radioactive isotope, which disintegrates spontaneously and it eventually becomes a stable isotope of some other element. So the radioisotopes that decay by emitting elementary particles such as alpha, beta, neutrons, protons, beta plus, or electromagnetic radiations such as gamma rays or X rays, or they undergo fission, that is breaking into smaller nuclei. So these isotopes, in some cases, they occur naturally as like 40K, D2, and 13C. However, most of them are also made artificially, or they are synthetic in nature, such as cobalt 60, cesium 137, zinc 65, and plutonium 239. Now, in radiochemistry or radioactivity, the parent nuclei is referred the parent is referred to the nuclide that undergoes the decay, and the daughter nuclide is referred to the one that is formed as a result of the decay of the parent nuclei. Okay, so the ratio of neutrons and protons, it is a clear indicator of stability in a nucleus, and that is why this ratio is very important. So if the atomic numbers Z of all the stable nuclei, they are plotted as a function of the number of nuclei present in the nucleon, then we obtain a graph that is shown in figure 12.1. As you can see in this figure, the x-axis, it plots the number of the neutrons, and the y-axis, it plots the number of the protons. So it shows, from this graph, it shows that the all the stable light elements up to Z is equal to 20. It require approximately equal number of neutrons and protons, that is mostly up to the atomic number 20. So although there have been certain exceptions like deuterium D2, 13C, oxygen 17, oxygen 18, fluorine 19, sodium, aluminium, and 31P, where sometimes this rule of Z is equal to N is not applicable. However, for heavier elements for which Z is greater than 20, more number of neutrons are required. So this deviation from N by Z is equal to 1, it occurs because the protons being charged particles, they repel each other, and this is in accordance with Coulomb's law. Now, since the nucleons, that is the particles within the nucleus, they are held together within the nucleus by very strong and short ranged nuclear forces, some additional forces they are needed to compensate for the coulombic repulsion that arises due to the protons repelling each other. So for stable nuclides, the N by Z, it varies in a wide range of 1 for calcium to 1.4 for mercury, as we can see the data that is given in table 12.1. So though N by Z is equal to 1 for almost atomic number is equal to 20, there are also certain exceptions. So here from table 12.1 we can see the variation of N by Z with increasing Z. Then there are also stable pair of nuclides with odd Z and mass numbers A. There are many stable nuclides which are also monoisotopic in nature. So there are various types of such types of stable isotopes. They have been further classified into four possible groups, and accordingly they have been named as even or odd depending on the number of Z and N, which is shown in figure 12.2. So from figure 12.2, it represents the classification of nuclides based on the number of their odd even number of Z and N. So if Z is equal to even and the number of neutrons, Z represents the number of protons and N represents the number of neutrons. If Z is even and N is even, then the A, that is the summation of Z plus N, is even. So the number of stable nuclides is, so here it is 100, 165. Certain examples have been given here is such as helium 4, oxygen 16, krypton 84, etc. Now when Z is even and N is odd, that is the number of protons is even and number of neutrons is odd, then the total A, it turns out to be odd. So the examples include oxygen 17, 25 mg, barium 137, etc. Now when the number of protons is odd, but the number of neutrons is even, then the total A comes out to be odd. And such examples include lithium 7, fluorine 19, copper 63, etc. However, when Z is odd and N is odd, then the A, it comes out to be even. And the examples include 5 cases like 2H6Li, 10B, 14N, and 50B. So here from this table, following we come across a few generalizations from this table 12.2. Looking into table 12.2, we find that when A is even with when for that the value of A remains even when Z is even and N is even, largest number of stable nuclides form with this combination. If we look into table 12.2, which represents that if Z is even and N is even, A is even, and the largest number of stable nuclides that come out to be the greatest in this case. Now, when A is odd, there are approximately the same number of stable nuclides with even Z as well as with NZ. So, if we look out when A is equal to comes out to be odd, if one of the Z and N is odd, then the number of stable nuclides is almost similar to each other, that is 50 and 55. For the third realization, we can see from table 12.2 that for both even A and Z For A remaining even with Z is odd and N is odd, only few stable nuclides are formed. Here, in the last case, if we look into table 2.2, Z is odd and N is odd. However, the number of stable nuclides that results is very less, that is only 5. So, based on these generalizations, two major inferences were made. First is the nuclear forces between two nucleons, they are independent of whether the nucleons are protons or neutrons. That is, the nuclear forces are independent of the type of the nucleons. The nuclear stability is more if Z and or N are even, and it decreases when either of them are odd or both are odd. So in general we call it as odd even effect. So the odd even effect, it indicates that the nuclear forces between two nucleons, they are not dependent whether they are protons or neutrons, and nuclear stability is more if Z and or N are even, and if either Z or N are odd, then the nuclear stability decreases. This is called as the odd even effect, which arises because of the pairing of the nucleus in the same shell. However, it is should be remembered that the pairing occurs between proton-proton and neutron-neutron, but never between a neutron and a proton. So it may be also noted that protons and neutrons, they occupy different shell, and hence the question of their pairing, it totally does not arise. Now, an odd Z and odd N nuclide contains at least one unpaired proton and a neutron, each in differentials and in differentials only, and they contribute little to the binding stability of the nucleus. Now, the nuclei not falling on this curve or with the N by Z ratio deviating from the expected ratio are very unstable, and they undergo decay by emitting characteristics radiations like beta minus, beta plus, or they capture electron of definite energy and half-life. If the unstable nuclide is on the neutron rich side of the plot, it disintegrates by beta particles, or they are called as the negatron because of the beta negative sign. And the daughter nuclide will contain one less neutron but one more proton on the nuclide. That is, if the parent nuclide X, it under with A and Z, it undergoes a beta emission, then it forms a daughter nuclide Y, where A remains as such, the Z, it becomes Z plus 1, and the N, it has N minus 1. So on the other hand, if the nuclide is on the proton rich, that is, it integrates by emitting a positron, which is a beta plus, and the process or by related process, which is electron capture. So in this case, with a beta plus emission or a positron emission or electron capture, the parent nuclide, which was X, it forms a daughter nuclide Y, where the A remains the same, the Z is decreased by one factor, and the N, it is increased by one factor. So for heavy nuclides with mass numbers in the region 200 or more, a more common mode of alpha emission is observed. The resultant daughter nuclide, it contains two protons and neutrons than the parent nuclide. That is, if we have a parent radionuclide X with A, Z, and N and its parameters, and it undergoes a alpha emission, then the daughter nuclide Y that is formed, it reduces the A by 4 units, the Z by 2 units, and the N by 2 units. So more commonly, the alpha and beta, they are they are accompanied by emission of electromagnetic radiation, but it is not always essential, as there are some pure beta emitters also. Now coming to discovery of radioactivity. The discovery of radioactivity was known, it was first discovered by the scientist Henry Becquerel, and from the emission of radiations from a uranium salt. So this phenomenon of spontaneous emission of radiation was called as radioactivity by Madame Curie, who later discovered two new radioactive elements, that is polonium and radium, and she was awarded the Nobel Prize twice for this discovery. The radio Fermi, Enrico Fermi, he first built the nuclear reactor and it paved the way and further production of radioisotopes. The radioisotopes that are used today, it is always benefit for people and society. So with this, however, we do also have negative influences of radioisotopes. Now coming to laws of radioactivity. So all radionuclides, they do not decay at the same rate. So looking at the kinetic laws, there are two laws of radioactivity. So according to first law, the rate of disintegration of a radionuclide at any time, it is proportional to the number of its atoms present at that time. That is given as minus dn by dt is equal to lambda n. So where n represents the number of radioactive atoms at a particular time t, lambda is the decay constant, which is characteristics of the radionuclide. So on integrating this equation 12.1 and putting the limiting values, we find n is equal to n0 into e to the power minus lambda t, where n0, it represents the number of the radioactive atoms that was present at time t is equal to 0. N0 minus n, it represents the number of radioactive atoms that have undergone the decay. So from the decay plot of radioactive elements with time has been shown in figure 12.12, which decreases with time. Therefore, this from equation 12.2, we can, using this equation 12.2, we have a final equation for calculation of T half, that is equal to ln 2 by lambda, which is equal to 0.693 by lambda. So since each radionucleotide has its own characteristic decay constant, so it has a definite half-life. So the mean life of a radionucleotide is given as 1.44 T half or 1 by lambda. The second law of radioactivity, it was proposed by Soddy and it is called as group displacement law. So this, according to this group displacement law, during a radioactive decay, the alpha emission, the parent decays to daughter where the Z is decreased by 2 and is displaced by 2 place on the left in the periodic table. Similarly, during the beta decay, the Z is increased by 1 and the nuclide is displaced by 1 position towards the right in the periodic table. So this is called as Soddy's group displacement law, which indicates the position of the daughter element that is formed after the radioactive emission. Now coming to units of radioactivity, it was originally based on the disintegration rate of 1 gram of radium and it was called as Curie and represented as Ci after Madame Curie, who discovered the word radioactivity. However, because of measurements in half-life measurement and other factors, it is now defined as the quantity of any radionucleotide that emits 3.7 into 10 to the power 10 disintegrations per second, that is dps. So now Curie being a huge quantity, the practical use has come down to millicurie, that is MCI or the microcurie, micro CI. So in reactor technology, curie, that is capital MCI, is more commonly used for in reactor terms. So the SI unit of radioactivity is becquerel, BQ, where 1 BQ is equal to 1 disintegration per second. That is 1 BQ is equal to 1 DPS. However, this situation was further complicated because 1 BQ is a very small quantity and there is a strong tradition of using CI more commonly. So mostly the unit of radioactivity is measured in CI or DPS. So it may be noted that DPS is often referred to as the activity of the radioactive sample, and it is measured as counts per second per minute as CPS or CPM. CPS indicates counts per second and CPM it indicates counts per minute. These are related by the equation epsilon into DPS is equal to CPS, where epsilon is the efficiency of the detection system. So a more useful parameter is the specific activity, which is defined as the activity per unit mass of the sample. So for typical radioanalytical experiments, only milli-CI or micro-CI has been used. Now coming to natural activity. So natural activity, it it is a spontaneous emission of the radiation, particularly from uranium substances, which was first discovered by Becquerel. Now other salts have also been found, such as thorium salts. Radionuclides have also been found in nature, such as 14 carbon 14, potassium 40, and others. Now coming to the decay series. So three naturally occurring radioactive decay series, mostly corresponding to two isotopes of urium, that is urium 235 and urium 238. They are two of the naturally common occurring radioactive decay series. Thorium 232 has also been identified as a natural source. So these radioactive elements, they successively decay to give different isotopes of lead. So the spontaneous emission, it keeps on occurring till a stable element is obtained. So these elements, they undergo successive decay processes, and by emitting different types of alpha and beta particles until a stable isotope is reached. Here the U235, that is uranium 235, the T half is 7.13 into 10 to the power 8 years. It decays to lead 207 by emitting 7 alpha and 4 beta particles. Similarly, uranium 235 to 238, sorry, which has a T half of 4.5 into 10 to the power 9 years, it decays to lead 206 and by emitting 8 alpha and 6 beta particles. So similarly, during the successive decay of each of these, different isotopes of elements having Z greater than 82 are obtained as intermediates. So these three series, they are also called as 4N, that represents thorium 232, 4N plus 2, which represents urium 238, and 4N plus 3, that is which represent uranium 235. They all have been isotopes. They are numbers which are divisible by 4 and remainder as 0, 2, 3 respectively, and that is why these three series, they are called as 4n, 4n plus 2 and 4n plus 3 series. Now the change in mass number in natural decay chain, it is because of the alpha emission, whereas beta emission is accompanied by a change in the increase in atomic number but no change in mass number. So another artificial decay chain is called as the Neptunium decay series, which corresponds to 4n plus 1 series. So final product of this extinct chain is bismuth 209, that is by emitting 7 alpha 4 beta particles. So besides two weak beta activities due to potassium 40 and rubidium 87 has been discovered by Campbell and Wood, even samarium 147 has been found to emit alpha particles. In recent years, several naturally occurring radioactivity with long lives have been found. So figure 12.3, it shows the natural radioactive decay series of uranium 235, which is also known as 4n plus 3 series. Figure 12.4, it shows the naturally occurring 4n plus 2 radioactive decay chain of uranium 238, and here in figure 12.5 you can see the natural radioactive decay series of thorium 232, which is also called as the 4n series. So these are the three types of naturally occurring radioactive decay series. Then the classification of nuclides. A nuclide which is particularly denoted as X to the power A and the subscript is Z, where X is the parent element. The superscript A, it denotes the mass number. and the superscript subscript Z, it denotes the atomic number. So so this element X, it has the number of neutrons is equal to A minus Z, which is represented, the number of neutrons is represented by N, and overall it can be represented like this. So, according to stability, all nuclides have been classified into five groups. Firstly, the stable nuclides that do not undergo radioactive decay, but they are found in nature. So, there have been about 275 such nuclides like carbon 12, nitrogen 14, oxygen 16, etc. Then come the second class, that is the primary natural radionuclides, which are found in nature and they have long half lives like uranium 238, potassium 40, and rubidium 87. The third category is the second natural radionucleotides. They are found in nature as decay products of the primary natural nucleotides and their half lives are very short, like thorium 234 and radium 226. Then comes the fourth class, that is induced natural radionucleotides, which are continuously produced by the action of cosmic ray on the Earth's atmosphere and hence they are found in nature. Common examples are 3H, that is tritium, and carbon 14, which are used in radioactive dating process. And the fifth is the artificial radionuclides that are produced by the bombardment of the nuclear particles on any target nuclei in a nuclear reactor. There have been more than 2000 such nuclides, and this process is called as artificial radioactivity. So, also nuclides have been classified on the basis of their atomic number, mass number, and Z, and number of neutrons. So, isotopes are a set of nuclides whose number of Z, that is their atomic number, remains the same, but their mass numbers are different. So, for example, hydrogen has three isotopes like 1H, 2H, and 3H, out of which the 1H and 2H, that is the proton and deuterium, they are stable, whereas the tritium, that is H3, 3H is radioactive. Then isobars, they are another class of nuclides that have the same mass number, that is the A remains the same, but the Z is different. Like B12 and C12, they are isobars in nature, and N12, they B12, C12, and N12, they have 5, 6, and 7 protons, and they are isobars in nature. They are called as isobars. Then comes the third category, they are called as isotones. The isotones are the nuclides. They have the same number of neutrons, but their number of protons are different. For example, carbon 14 and N15 and oxygen 16. They all have 18 neutrons in them, but their Z is different. So that is why these three are called as isotones. The next classification, the type of nuclides, are the nuclear isomers. The nuclear isomers, they are the nuclides which have the same Z and A, but they differ in their nuclear excitation states. Thus, they have very small half-lives and they are designated by using M, small m, which means metastable. For example, bromine 80M and bromine 80, it indicates that one is an isomer in a nuclear state with a different half-life. So this is all about the classification of various types of, we come across the various types of nuclides the in radioactivity. So with this, we finish today's class. We'll continue with the remaining part of radioactivity in next class. So if there are any questions to ask, please ask. Please feel.
No, ma'am.
Okay. Then this much for today. We'll cover the remaining part in the next class. Thank you.
Thank you, ma'am.